So all of the faculty of this school are involved in hands-on science, small-scale, hands-on tabletop experiments. I'm going to speak mainly about some of the experiments we've done in my laboratory in Texas, but other faculty would give a similar sampling of hands-on science from their own experience. The work I'll talk about was done by, of course, by the students and postdocs in our group in Texas, and a representative of that group is one of the instructors here in our hands-on session on fluid patterns, Michael Alshaus, right here. So let me contrast what we do with what you read about in the newspapers and hear about on television and see on the internet and YouTube and so forth. And that's mostly big science. Big science gets big attention. The Large Hadron Collider, as everyone in the room knows, was used to make a marvelous discovery of a particle predicted 50 years ago. It was a culmination of the understanding of the standard model, the Higgs boson. So 3 years ago this week, this particle was announced as having been detected at the Large Hadron Collider. Another big science project is the James Webb Space Telescope. It's been under design and construction for 20 years at this point. Will cost more than $10 billion. This is a character of big science. A lot of money is involved, several decades typically, and typically thousands of scientists. So the James Webb Space Telescope is designed to look back at the very early universe and give us a better understanding of the cosmology of the early universe. Another project which is under construction is the ITER project in Cadarache, France, which is a large plasma physics machine designed to produce fusion, nuclear fusion. It's a model for ultimately building fusion reactors that would provide electricity without adding carbon to the atmosphere. So these are all very important projects at the apex of science, research and discovery, but it's possible to do science on a different scale, and that's the subject of this school, where the cost is not 10 to the 10th dollars, but more like 7 orders of magnitude smaller. And the time scale is not decades, but a year or 2 or 3. And instead of having thousands of scientists involved, you might have 1 or 2 or 3 involved in a project. So this has become especially possible in the past decade or so, past couple of decades, where electronics, because of the drive of consumer demand, has become very cheap. You can use the webcam that's maybe in your cell phone or buy one. Computer interfaces that were not so long ago many thousands of dollars are now very cheap. And especially computing for acquiring data, analyzing data, doing numerical simulations. The power of a laptop like this is comparable to the power of the largest supercomputers just 2 decades ago. And the amount of storage that one can have for less than $100 is incredible by the standards of a decade or 2 ago. So this makes it possible to do serious science, forefront science, at a relatively small cost. Now, I want to consider systems studied in this way, in tabletop experiments, especially systems that are taken away from the thermodynamic equilibrium state. Suppose we have a system in thermodynamic equilibrium. We have a gas in a box. And the gas is at a constant temperature. The box is at constant temperature. Molecules are bouncing around in this fluid. And the One molecule affects others only if they're nearby, within distances of nanometers. But if we put a temperature gradient on the box, heat the bottom, so its temperature at the bottom is a little larger than the temperature at the top, then of course heat flows from hot to cold, and you have heat flux. Now if the temperature gradient is small, the heat flux is conducted through the gas, and there is no motion of the fluid. The fluid on a macroscopic scale stays motionless, and still a molecule only affects molecules that are nearby in the fluid. But if we increase the temperature difference between the top and the bottom above a certain critical value, you have the onset of convection rolls, where the hot fluid will rise, say, and then it will go, the cool fluid will go down, and you get a convection roll. And now if a molecule here has an average velocity downward, you know that a molecule that is a certain distance away will be correlated to that velocity. You now have long-range correlations. If you had an infinite box, in principle, you'd have infinite correlations. Now, we can ask what happens if we try to predict that onset of convection as you increase the temperature difference. And that was a problem that was addressed in about a century ago now by many scientists without success. They said, let's take even a simpler problem. We have two parallel plates with a fluid contained between them, and we move one plate, keep the other plate at rest. And can we predict when there will be a transition from this base flow, the flow where the velocity is just varying linearly from the bottom to the top plate? And many of the great scientists of the early 20th century attempted to solve this problem without success. But another system, another geometry, was considered by an Englishman, G.I. Taylor, in that time period. He said, let's consider a fluid contained between two cylinders and rotate one or both cylinders and look at the fluid and see when there's a transition in behavior. And when you solve problems like this, where you're very close to equilibrium, the gradient is small, the solution, you can prove, there's a theorem, has the same symmetry as the boundary conditions. So here you're rotating the inner cylinder, so if it's small rotation rates, you know a parcel of fluid is just going to move in a circular path. But above a critical speed, he found in experiments first, tabletop experiments, that a pattern forms. And this pattern was observed by injecting ink into the fluid, and he could see lines above a certain rotation speed. Horizontal lines appeared, and those were interpreted as boundaries between vortices that encircled the inner cylinder and were stacked along the axis of the cylinder. So then Taylor set out to calculate the point at which this instability would occur. There would be a transition in the behavior. And could he find, through analysis, a well-defined rotation rate of the cylinder at which this would occur? And the answer is yes. He calculated now, with both cylinders rotating, you have on the vertical axis here the speed of the inner cylinder, on the horizontal axis the speed of the outer cylinder. So right here at 0, both cylinders are at rest. That's thermodynamic equilibrium. And he calculated the points that are shown here that are the green points. It was a very tedious calculation. He had no computer. It was done by hand, and he had several people check the calculation. But he did these experiments that gave points which were in remarkable agreement. They fell within a few percent along the line he obtained theoretically. So this was the first success in calculating the onset of instability as you take a system from the equilibrium state by imposing some gradient in concentration or gradient in velocity or temperature, calculating the point at which it becomes unstable. And here are some of the people who had tried previously and failed. You've heard of the names, Lord Kelvin, Lord Rayleigh, and so forth. But this work proved that you could calculate, demonstrated that you could calculate the onset of instability, also demonstrated the validity of the equation of motion for a fluid, which is called the Navier-Stokes equation, and the validity of the boundary conditions, that is, that the fluid doesn't slip at the boundary. Now, later on, an experiment was done with the speed of the cylinder rotating faster, and you could see as you rotate the cylinder faster, here you have the vortices, which we call Taylor vortices after G.I. Taylor, which are time independent. But you rotate the cylinder, say the inner cylinder, faster, and at some point you get that these time independent vortices become unstable, and you get waves that travel around the annulus. And here's a photograph, a movie of these. And as you increase the speed of the inner cylinder higher, you get a transition to irregular behavior, something called chaos or chaotic behavior, and ultimately to turbulent behavior, where you have a wide range of spatial and temporal scales. Now, if these data in the previous picture are analyzed, you measure the velocity as a function of time, and then take Fourier transform of the velocity time series, modulo squared of the Fourier transform is the power spectrum. You can see how these transitions appear in the power spectrum. Here, if you have one frequency, a wave going around, you can see the frequency of that wave. In our lab that Michael Alshouse and I will be leading, we will use a webcam to make movies and obtain power spectra from the digital movies. And we obtain spectra like this, where you have a single frequency component where you have the waves traveling around the annulus. As you go up in rotation rate of the cylinder, you get the higher critical rotation rate, where there's a transition, a bifurcation in the solutions, and you get a second frequency appearing, and you get a lot of other stuff. But all of these other peaks correspond to sums and differences of these fundamental frequencies. You go yet higher in rotation rate, higher Reynolds number. At the time this experiment was first conducted, the expectation was that you would get a third discrete frequency and then a higher transition with a fourth and so forth. But that's not what was found. What was found was that noise appears here in the spectrum. It was first thought to be instrumental noise, but after some careful tests, it was decided this must be inherent to the fluid, a property of the fluid. So after you have two frequencies, you get a transition to a state which is not periodic. It has this broadband noise, and it's a state we now call chaotic behavior. And so in our laboratory, then we looked at another system, a chemical system, a homogeneous chemical system. So chemicals are pumped into a tank and are well stirred, so the concentrations are uniform throughout. And you could vary the concentrations of the chemicals coming in, or you could vary the flow rate. And you see for some range of input concentrations in this reaction known as the Belousov-Zhabotinsky reaction, you get simple periodic oscillations. But we found that beyond a certain concentration of the input chemicals, you get this oscillations. This is one of the products of the reaction, this reaction of bromide ion concentration. And you can see it's oscillating here in time. But if you look at the successive peaks, you see that the signal is not just repeating. It has a periodicity or oscillation to it, but it's not periodic. And so to analyze that, we look at a plot where we have the bromide ion concentration at some time t here, and here the bromide ion concentration at some later time t plus tau, and plot that, and we'll see, let's see. So here's a movie that was made 35 years ago on a 16 millimeter film, and you can see now in this two-dimensional plot, this point in a phase space represented by the concentrations at 2 times, that you have this orbit here. If we draw a line here and let the value of the y-coordinate when it crosses the line be xn, we can then make a sequence of points on a graph of xn plus 1 versus xn. And the interesting thing about this plot is that we know the flow is not periodic. It gives, if we take the time series and take a power spectrum, we have broadband noise. If we look at the oscillations in the time series record, they never repeat. Yet, given xn value here, we, from this curve, can read the next value. The system is deterministic, but not periodic. And that's chaos. That if you take 2 points on this curve here, which are arbitrarily close together, they separate exponentially fast in time. The characteristic rate of separation is given by an exponent, the Lyapunov exponent, which characterizes how chaotic the system is. So this is another picture of results from that experiment where we construct a picture in phase space. This is a two-dimensional projection of a high-dimensional graph, and then we can calculate properties of this chaotic behavior by different methods, which were reported in several papers. Now, Turing, who everyone in the room is familiar with, from the movie Imitation Game, if not elsewhere, the Turing machine, fundamental computer, the Turing machine, or from the Turing reaction, and wrote a paper entitled The Chemical Basis for Morphogenesis. He was interested in how do patterns, how there's a morphology, how there's a pattern, form in a biological system. And he was a mathematician, so he didn't have a complicated biological model. He had a chemical model, a very simple chemical model with a chemical reaction, different species reacting together, and the species diffused at different rates. The different chemicals had different diffusion coefficients. And he solved that model, and he found, if you solved it in space and time, where you have diffusion and reaction, that you could reach a critical value of the concentrations where a pattern would spontaneously form in space. And that's called the Turing pattern now. And his idea was that this might be a way of understanding how pattern forms in biological systems. Now, that's a whole subject of discussion and debate even today, but this model system clearly showed the instability of the homogeneous state leads to the formation of a pattern with a characteristic scale. Now, there were experiments searching for such a pattern, but one had to build a system which would maintain a non-equilibrium state in which you could impose different gradients to get different distances away from equilibrium. We built one together with a group from Bordeaux that would give us this condition. So we'd feed oxidizing chemicals into one reservoir, which was continuously refreshed. You can see the flow. And reducing chemicals into another reservoir. There is no reaction in either of the reservoirs, but the chemicals can diffuse into a very thin gel layer. And there you have an oxidation-reduction reaction. And you can look through the top of this reactor, through the transparent chemicals, and see if the concentrations within the gel layer are uniform or not. And what was found was that above a certain critical value of the concentrations, a pattern spontaneously formed. and it was stationary pattern. This is the pattern. And characteristic distance between the two spots here is in the situation for this experiment, 0.2 of a millimeter. But from Turing's theory, you could calculate the separation between the spots if you know how fast the chemicals diffuse, diffusion coefficient, and you know a characteristic time associated with chemical kinetics. And those were independently measured in this experiment. And taking this product here in the square root, you measure a length, which is just what was seen in the experiment. So this is a Turing pattern, a two-dimensional pattern formed by a chemical system. Now, the approach that Taylor took and Turing took to finding the onset of a pattern was to consider the uniform state that you have near equilibrium. If the boundary conditions are uniform, then the base state near equilibrium will be uniform. And then consider what happens as you move away from the equilibrium state, or from the uniform state, by the imposition of a gradient which is increasing in size. And in that analysis, you're solving an eigenvalue equation, and that gives you the solution will give you the growth rate of a disturbance. Now, if you're near equilibrium, that growth rate is negative. That is, any perturbation will decay. Any disturbance of the system will decay, and you're left back with the uniform state. But above a critical distance away from the equilibrium state, you have the perturbation, however small it might be, infinitesimal perturbation, will grow, and you form a spatial pattern. And so that was the kind of analysis conducted by both Turing and by G.I. Taylor, and it's the kind of analysis one can now understand could be applied to all kinds of systems that are driven away from thermodynamic equilibrium. So the growth rate of the disturbance has a dependence on the length scale. So this is the growth rate plotted for some distance below the instability here, and it's always negative, meaning the disturbance decays. At some, as you increase, say, the rotation rate of the cylinder here, you reach a critical value where the growth rate is not negative for all lengths. There's one length scale where the growth rate is 0, and just slightly higher Reynolds number, this perturbation, instead of decaying, will grow. And you form a pattern. In the case of the flow between the concentric cylinders, this is the axial array of vortices that encircle the inner cylinder. So this approach to the solution of instability is called just linear stability analysis, and can be applied to many systems, wide range of systems, to find the point of instability where a pattern forms. Now, that growth rate I've shown was a real number. That eigenvalue can be a complex number, in which case, instead of having a stationary pattern, you have traveling waves. Here you see traveling waves. This is an oxidation front here, and it's traveling. Two waves that were here have collided and annihilated one another, and you can see them traveling. Now you can get such spiral waves in situations that occur in the heart. Normally you have a pacemaker that sends out electrical pulses to pace the heart from the sinus node here, and travels down, and you get the beating of the heart in response to that electrical signal. But sometimes when you get old or you have some disease, these pathways might be broken, and when the pathway of conduction from the sinus node out to the heart chambers is broken, then you can get spiral waves in the heart. And they lead to very rapid beating of the heart and to cardiac death, fibrillation and death. In the United States, there are more than 100,000 people a year who die from the formation of these spiral waves. Okay. Well, here's another example of where a pattern forms that was observed a century and a half ago by Michael Faraday, who, of course, made many discoveries in physics, but he had looked at an oscillating dish of liquid, like water. You oscillate a pan up and down, and the layer surface remains flat if the amplitude of oscillation is small. The maximum acceleration is below a critical value. Above a critical value, you get the spontaneous formation of a wave on the oscillating liquid layer. Now, to actually solve this problem in stability took many years passed, and Professor Tuckerman, who was a member of the school faculty last year here at the hands-on school, it was the first person to actually solve this problem mathematically, and she'd done some further recent work where she found the onset of instability. The amplitude of the acceleration is necessary for a spatial pattern to form on the surface of a vertically oscillating liquid layer. And some experiments were done by Golub and co-workers of oscillating layer, and depending on various conditions, the thickness of the layer, the viscosity of the fluid, and so the pattern can have different forms. Here's a hexagonal pattern like the one we saw for the Turing pattern, and here's a stripe pattern, but he also found a pattern that had two characteristic frequencies, spatial frequencies, but the pattern itself was not periodic. It's a quasi-crystalline pattern. Very interesting. Now, some work done by a number of people, particularly Mark is here. Professor Mark Shattuck, you know, the guy with the ponytail, the hair in the back but none on top. Okay. He's done some work on this system where you oscillate a layer of grains of particles. And if you look at the layer of oscillating sand, below a certain acceleration of the oscillating container, the layer remains flat as it flies up in the air and comes back and makes impact with the container. Every oscillation, it just remains flat. But above an acceleration of about 2.6 g, you have an oscillating container, so that's the maximum acceleration per cycle. Above about 2.5 times the gravitational acceleration, then the layer is going up in the air for part of the cycle, since the acceleration exceeds g. When the layer goes down the container faster than g, the grains remain in the air. It found this pattern forms, and this is looking at it on a large scale down at the layer that is in a container oscillating up and down. It's a photograph, and you don't see any particles here because they're too small to see. This is 1,000 times the particle diameter. But if you look close up, you see the individual grains of sand in a snapshot. One oscillation of the container later, where you have a black region here, you'll have a white dot like this. Two oscillations of the container later, you'll have the same pattern with the same orientation. Now, in work that Mark Shattuck and others did, they used molecular dynamics, and that's the topic of his hands-on session, molecular dynamics simulations, where you just apply Newton's laws to particles which are flying through the air. So when they collide, they exchange momentum, but momentum of the system is conserved, and they also conserve, in these collisions, angular momentum. In the collision, though, there's a little bit of dissipation. The particles are slightly deformed, and you lose a little energy. Between collisions, if the experiment is done in a vacuum, particles move in a parabolic path. And this is what was found by comparing experiment and simulation. These are, in the experiment here, a photograph, a snapshot of an instant of time, and this is the result from the simulation. molecular dynamics simulation. You can see the agreement is quite good. This is here are the details for the conditions of the experiment, and you can see the oscillation frequency is 15 hertz. If the oscillation frequency is changed, the pattern can change. And here is at 25 hertz, you see in the experiment a pattern which is basically stripes. You have some effect of the walls. If you had a very large container, you would see parallel stripes of particles. And similarly in the simulation. We used a small container because the simulations in this case were done on a laptop computer and could only handle 60,000 particles. If you did the calculation on a supercomputer, you could handle a lot more particles. So here you see Mark Shattuck's name. Chris Bison, the first author, was a graduate student. Okay, and under some conditions in this experiment, when you're oscillating the container of particles vertically, it was observed that instead of there being a pattern which spread throughout the whole container, there would be just a local oscillation with a peak that would go up and then go down with the oscillations of the container. And Mark Shattuck made a nice movie of this. You can see the peak, crater, and the rest of the whole layer is flat. And this we called oscillons. Actually, Eric Weeks is responsible for this term because we were sitting around the table one day wondering what to call these localized, oscillating, non-propagating, dissipative structures, and Eric Weeks said, oscillons. So that stuck, and now if you look up oscillons on Google or someplace, you'll find many people have observed oscillons in different kinds of systems, in DNA chains, in chemical systems, in ocean, a wide variety of systems. Exhibit these localized dynamic structures, non-propagating structures. Let's see, how am I doing at the time? Okay. Well, I'll do this quickly. Now, suppose instead of oscillating grains, we oscillate a layer of cornstarch. Cornstarch behaves peculiarly. Its viscosity depends on how fast you move an object through it. You know, if you're stirring cornstarch in water slowly, then it stirs just like a thick fluid, something with large viscosity. But then if you try to stir fast, it becomes stiff. The little particles in the cornstarch, the grains that are in it, get jammed together, and that's called shear thickening. And then, so it has this peculiar behavior. So an experiment was done by Robert Deegan to look at this, and
here you see a stick in the liquid, and it's stirring it around with some cornstarch and water. Stir that water, stir that cornstarch. Look at it dip. Dip and swirl. That's the good stuff. Now once you add some acceleration to the cornstarch,
so it just accelerates faster.
You see the pulsating waves commence to pulsating. Yeah, pulsate, baby, pulsate.
This is a YouTube video, as you might know.
Look at that shake. All right, here's the holes. Now once it's pulsating, you grab a little can of air, you blow some holes into the mixture.
Or you can just stick your finger in the mixture.
Yeah, but then the holes just stay on being holes. Look at it again from the top view. Ooh, hit it. Cornstarch holes. Yeah, that's the good stuff right there. Pulsating cornstarch holes from the liquid top view. Look at that. Yeah. Oh, yeah. Yeah. Holes. Pulsating holes. Now here you see 3 holes, and 2 of these holes are doing their own thing. One of these holes is not. Can you tell which one is not doing its own thing? Street Revisited. Ooh yeah. Hit it. Hit it. And then here's where the holes grow fingers. Once you turn the frequency up a bit more, the holes no longer appear to be holes. Instead, they turn into fingers that multiply into more fingers and the more fingers until completely consuming the cornstarch dish. Ain't that fascinating? Ain't that fascinating? Fascinating. Look at them grow.
Okay. Well, that experiment we know has been done now since the videos on YouTube by many high school students for science fairs, maybe thousands, because I get emails from them. So now let us consider what happens if we go beyond the onset of instability as we take a system away from the equilibrium state. So here we have the same graph we had before, where this is the speed of the outer cylinder, where you have a fluid contained between two cylinders, and this is the speed of the inner cylinder along the vertical axis. And what we looked at previously was the Taylor instability given by this black line right here. Now, David Andrich looked for higher rotation rates of the inner cylinder and observed many different states. This is like a phase diagram for some complex solid material, except this is a fluid, and this is not in equilibrium. You're driving the system away from the thermodynamic equilibrium state. And in the session that Michael Alshouse and I will have, we will take the system along this axis and look at some of these states that occur when you increase the speed of the inner cylinder. Now you can go to larger scales and still do laboratory experiments. Now, the experiment inspired by the great red spot of Jupiter, which is here, was observed by Robert Hooke more than 3 centuries ago. On May 9th, 1664, 9 p.m., he looked through his telescope and he saw this big spot on Jupiter, and he reported it in the very first issue of the very first scientific journal, Philosophical Transactions, Royal Society, a big spot on Jupiter, and he stayed up all night watching it move around and calculated the period of Jupiter. Now we have spots like this is a big storm. Big, I mean this distance from here to here across the spot is twice the diameter of the Earth. But we have vortices like that are hurricanes or high pressure systems or low pressure systems, and they form on the Earth or in atmospheres of planets and last for maybe a week or 2 weeks, or to the outside you might have such a vortex lasting for a month. The question is, how can this vortex last for centuries when others decay? And we considered the various physical mechanisms that were contributing to the formation of the spot and designed a tank to reproduce these basic physical mechanisms where you have a turbulent flow, a strong rotational effect, Coriolis effect, and not only is that effect strong, but it varies with latitude. Coriolis effect is a maximum at the poles and 0 at the equators, and a strong shear to make the turbulence. And in this experiment, then, for a range of conditions, we found a large single vortex would form. It's very dynamic. It sheds other vortices, small ones you can see, and it's continually consuming other vortices. So it provides a laboratory model for how such a large storm could persist in time in a tabletop experiment. Okay, now I want to talk a little bit about growth processes, changing the subject a bit. Suppose you have an oil layer between 2 glass plates here, and the oil layer has a bubble of air in the middle. If you increase the pressure on the air, the bubble will grow. If it's a circular bubble and you increase the pressure very slowly, the bubble will just grow in size and remain circular. But if you increase the pressure faster, then you see this is the black is the air penetrating into the oil. It doesn't grow as a circle, but it grows into this complex structure. It's something we and many other people have been studying for a number of years. Here's some papers. It's, again, a tabletop experiment. It's a small experiment. And if you look at the structure here and think about what is the dimension, well, it's not a line, and it doesn't fill space as area. It's something in between. And the idea of some geometrical object having dimension in between integers goes back to 1927. Lewis Fry Richardson measured the length of the coastline of Britain with a certain measuring stick, 200 kilometers long, and he got a length 1,260 kilometers. Then he took a smaller measuring stick and looked at a big map, and he got a larger length. And then he systematically went about this, and he found that if he looked with finer and finer scale, the length became longer and longer without limit, and you could plot it on a log-log plot and get from the slope of that the dimension of this line. It's not an integer, it's something between 1 and 2. And he found 5/4. Now, in 50 years later, Mandelbrot became very interested in non-integer dimensions of physical quantities. There'd been some mathematical work done, well, going back almost a century, but just as pure mathematics, this is relating this non-integer dimension to physical phenomena. And Mandelbrot gave the term fractal to mean non-integer dimension. And for this particular structure I just showed, the fractal dimension is 1.71. Now, in another experiment, we looked at the growth of metal deposit electrodeposition. See this electrolyte here, zinc sulfate solution, and the switch is open. If we close this switch, close the switch, and you grow this zinc deposit, which is not smooth electroplating, but has this structure, and it happens to have a dimension about the same, 1.7 fractal dimension. Now, more recently we've been looking at the growth of bacterial colonies where bacteria are deposited in a drop of water on the surface of a gel, and they can move. Let's see, they should move. They're motile, they move in time. There they move. Yeah, they're swimming. These are bacteria, in this case, that are 7 microns long. You can see them swimming. And they are reproducing, and they form a colony. You start with a little droplet, and it forms a colony. And interestingly, has about the same dimension. But we became interested in the growth of this colony and studied that. But this is a hands-on school, and we haven't done anything hands-on yet, so it's time to do an experiment. Michael, let's see. Every third person or so, take a sheet here of this black plastic. Let me divide. You give them out here. Could you give them out on this side? So share with another person, and because you're going to do an experiment together. It's good to do experiments with others where you can check what you observe and interpret it. Now you note the plastic has a plastic sheet. This is from the trash can in my office. There's nothing special here. My office in Texas, that is. All right, so you can take the little sheet with the slit at the top. The behavior is different if you go in the perpendicular direction because the way the plastic is rolled out. but let's just take it this way, and we're going to tear the sheet in half, but let's do it together. So you want to grab the sheet firmly with two hands on the side and a little slit at the top, and slowly tear it apart. This is not a very good example, but tear it apart. And what you want to look at, go ahead, tear the sheet apart, all right, and look at it with your neighbor and describe to your neighbor, what do you see? What do you see looking at the edge that has been formed by tearing the two sides apart? What do you see looking at that edge? Talk with your neighbor. There you go. You've done this before.
Yeah, I've done this before.
Okay. Now, when you tear it, the plastic stretches. The plastic stretches. If you imagine a grid that was on the plastic sheet initially, now the points that are near the edge, which is torn, are further apart. You have modified the metric described by the grid that was initially on the sheet. You stretch the points apart. And if you look now at the edge, this is a photograph of the edge of a plastic sheet torn just as you tore it. And you see a section here which is 30 millimeters long. Now, we take this little section and blow it up, magnify it to make it the same size. Now it's only 9.6 millimeters from one side to the other. And you may note there's a similarity to what we had initially. And you can do this again, magnifying this little square that's up here by the same factor 3.2. It looks rather similar, and we do it again and again. And you get down to the point where the thickness that you see here, you don't see quite the structure, and that's because you're looking at the thickness of the sheet, which is maybe 40 micrometers. All right? Or it's less than 40 micrometers, because 80 micrometers all the way across here. So this is more like 8 micrometers. But you see this structure, which is the same on different scales, and you have waves within waves. And by the way, the dimension is about 1.7 here of this fractal. And then we can look at the stretch as how much is the plastic been stretched as a function of distance from the edge. Now, for different pieces of plastic, we could have a lot of stretch or less stretch, depending upon the plastic material. For this piece of material, the stretch function looks something like this. Near the edge, points that were separated by unit 1 in some units are now stretched 1.8 times as much right at the edge where the tear occurred. And the function goes off like this. But if you have another piece, and you get this fractal structure. But if the function is slightly lower stretching and falls off faster, then what is found is you only get two waves. Waves within waves, but no more. You don't get the infinite cascade. And if the stretch is even less, you get only a single wave. Now, go to the grocery market, look at leaves of lettuce and other leafy vegetables, and you'll see all three examples in the lettuce leaves, in the leafy vegetables. If you look at kale, for sure, it's a fractal. Kale. And then the question scientifically arises, what are the necessary conditions on this function, that is the total amount of stretch and the first and second derivatives, that are sufficient so that you get the fractal structure? That's an unanswered question in mathematics. There are a number of mathematicians working on that problem. And there are also geneticists working on different plants, because it's advantageous in some situations to have a fractal structure where you collect more sunlight or more water, more surface area. And if the plant, you might be able to get it to be more hardy in a dry climate. So there's a whole program in Europe to study, it was based on work that was done. This was all initiated by a postdoc who was working in my lab, and he's now the director of that European program, which has mathematicians, geneticists, and physicists working on this stretching that occurs even in the organelles. You have the endoplasmic reticulum, which has lots of wrinkles in it, so it has a lot of surface area. Other organelles are inside the cell, do not. So this is a problem in itself. Now we can, as I mentioned, leaves. Here's the beet leaf looking edge on, looking from the side. And here's a flower. And another experiment took a tube which expands in size if you dip the end into water. And if it expands enough, it wrinkles. And there you can see how a daffodil forms its irregular edge. Okay, now in doing hands-on experiments, as in doing all of science, you try to look for similarities in different kinds of phenomena to gain a broader understanding, as Newton did, looking at the apple falling from the tree and thinking about the law of gravitation and saying, well, if this law of gravitation applies to the apple falling from the tree, maybe it applies on very large scales to the planets. And you know the story. So that kind of thinking motivates a lot of what we all do in science. How can we unify our understanding of diverse phenomena? Now, here are diverse phenomena that we don't understand, but there is a suggestion of something that is common or universal in these different phenomena. Now, one last example, I guess. What about the behavior of fish in schools or, say, zebra in herds in the Serengeti, or birds in flocks? There was a beautiful study. It was done in Rome a few years ago by Cavagna et al. Of starlings that nest along the Tiber River.
Starlings work together to create the most astonishing aerial display in nature.
This is a BBC movie. Look how sharp the edge of these flocks is.
L'ho riprese. Quando mi ripigliava.
For those of you who are Italian, that means something. Okay. So these scientists measured the position of every starling within a flock as a function of time. That took multiple cameras. The starlings all look rather alike, right? To keep identifying them and following them, tracking them in time is not easy. Beautiful experiment. And then they measured correlations between neighboring birds as a function of flock size, and they found, depending on what they were correlating, they found the same sort of very simple functional dependence, one with no characteristic length scale, scale independent. If they correlate on the orientation of the birds or on the speeds of birds as a function of the separation, they found the same function, which is simply the correlation length is 1/3 the flock size. Very simple. So we were studying these bacteria viewed through a microscope, and you can track these. So the arrows indicate the direction and the velocities. Now, the bacteria don't have a nervous system. They can't see one another, so their interaction is very different from that of the starlings. They're also in 2 dimensions, not 3 dimensions. They're just on the surface. And their Reynolds number, their hydrodynamic interaction is quite different, because their Reynolds number is much less than 1. That means inertia plays no role. If they stop swimming, if the little flagellum stops rotating, then they stop immediately. Whereas birds have inertia, which is important. If you stop flapping the wings, of course, they can glide. So it's a very different kind of interaction. So we wanted to apply the same type of analysis that was applied by the Italian group. And to our surprise, we really expected to see something different. But the results for the bacteria under a variety of conditions follow closely the line that was found for the starlings. And we have no explanation, but again, it's an example of a suggestion of universal kinds of descriptions mathematically for very different kinds of phenomena. So, I'm going to conclude, considered systems that are forced away from the equilibrium system state and patterns spontaneously form. Now, in equilibrium systems, you can calculate some thermodynamic potential function or free energy and find the extremum of that function to find the behavior of the system. There's a systematic way of doing it. For non-equilibrium systems, there's no such thermodynamic potential function, and no function is known. There's no extremum principle known. Now, people, since the early systematic studies of systems driven away from equilibrium in the 70s, 80s, 90s, there was a lot of talk, if you go to conferences, about calculation of the appropriate thermodynamic potential-like function that would give you the state of the system if you took the extremum. But nobody's been successful. Maybe some of you young folks will be, right? If you are, you get a free trip to Stockholm to pick up your Nobel Prize, right? So there is no general theory, so we look at different systems and model them mathematically and perform quantitative experiments to understand general principles or get hints of general principles. And we see, we see from a variety of systems which have been studied by the various faculty at this school some hints of universal principles guiding their behavior. I could go on for a while, but I won't. I'll stop there. Thank you.